All right. Real quick, I'd like to show you evaluating this integral. I'm trying to give you a lot of practice seeing integral evaluation because I feel like some of these integral tricks can be rusty for everyone. So if I want to evaluate this integral, I know that I'm going to have to use u sub because there's a square inside of a square root that I don't feel like dealing with. So if I take u equal to 1 plus 4r squared, then I'll get du equal to 8r dr. That's just from taking this derivative and then saying there's a dr left over. So if I'm trying to get rid of an r dr, like I see right here, I know that r dr is equal to du over 8. So I can make a substitution. I'm going from 0 to 2 pi. Let's see. Square root u du over 8. And last time I did a u sub, I left the bounds blank and then I subbed them in later. This time I'll go ahead and do it the other way. So if I start with 0, then if I apply my formula 1 plus 4r squared, that becomes 1 plus 4 times 0. So 1. And if I had r equal to 2 before, that becomes 1 plus 4 times 2 squared. So that's 4, 16, 17. 2 times 2 is 4, times 4 is 16, plus 1 is 17. So my new bounds of integration are that I'm going to take this from 1 to 17. And if I do it this way, I don't have to switch my u back. If you prefer to switch your u back and then plug in your original bounds, do it that way. I just wanted to show you both ways for the two different ways that people solve this problem. So my 1 over 8 can come out front. Oops, my d theta should still be there. And I'm evaluating from 1 to 17, u to the 1/2 du. D theta hangs out where it was before. So u to 1/2 integrated becomes u to 3/2 times 2/3. Because then when I take a derivative, those cancel out and I get back down to 1/2. Great. And then I'm evaluating that from 1 to 17. D theta goes out front. So I've got 1 over 8, integral from 0 to 2 pi, and then it's going to be 2/3 times 17 to the 3/2 minus 2/3 times 1 to the 3/2. And I don't know what it is, but it's definitely a constant number. And then when I integrate d theta, it just becomes theta again. So let's see. 2 over 3 times 8, I'm just pulling out the 2/3 times 17 to the 3/2 minus 1 to the 3/2. I'll just do this on a new slide. Okay. I had 1/8, 2/3, 17 to the 3/2 minus 1 to the 3/2 is 1. Integral from 0 to 2 pi d theta. So I'm going to get 1 over 12 here. 2 and 8 cancel out to a 4. Still don't know what 17 to the 3/2 is. Integral d theta becomes theta evaluated from 0 to 2 pi. So that's just going to be 1 over 12, 17 to the 3/2 minus 1 times 2 pi. 2 and 12 cancel out a little bit to give me, we'll just call this pi over 6 times 17 to the 3/2 minus 1. And your book does not calculate what 17 to the 3/2 is for us, but they do tell us that this is about 36.18 square units. So you could plug that into a calculator. I don't know what it is. And then real quick, let's just note that the first problem we had, we could have solved with like geometry to find surface area, but this problem we really couldn't solve using tools before this class. So we can do old things with the surface area formula, but also new things.